does not mean that's all. Short talks, research in these AI centers developments will be very relevant for those who are interested in AI. They say that these are the dreamers who move the world. Many researchers are dreaming about super capabilities, the possibility of forecast the properties of materials and instance and different materials, and do not work without knowing that. I would like to invite Alexander Shapeev. Alexander works in computer technologies to resolve tasks with large arrays of data in Skoltech. Alexander is going to talk about artificial intelligence for modeling of new materials. Hello, my name is Alexander Shapeev. I am I'm associate professor in Skoltech and the modeling of materials. Now, the first question that you might have: why do we need modeling of materials at all? And the first answer to this question is that the modeling of the materials is something that replaces the experiment. Now, why it can do that? You can see it on the slide. You have the cost of the computation, the speed of the computation, and how it was changing in the last 100 years. And we can see that it increased by 16 times. And in 70s, it was enough to calculate some simple structures and the features of the flying machines. And by 2000s, it was enough to make some computational experiments to create materials. So this threshold was achieved. The computer experiments became 1,000,000 times cheaper, and it is now used to replace materials in experiments. The second question is, if we develop a material on a computer, we want to check it instantly on a computer. Because when we develop a material, we do not want to call the experimentation department and ask them to fit in their experimentation schedule to check whether our theory is correct or not. We would love to have the result of the experiment in seconds. The classical experiment is still the main method for the development of the materials. As an input, we have a composition and the synthesis plan of the material. The experiment is done in the lab, it is tested there, and then it goes on and on, different cycles of attempts and to develop a new materials. It goes back and then goes back to the lab. Now, if you have recently completed the data analysis courses, you would see that the outcome are data. Based on data, we can build an ML model, and based on the input data of the experiment, we can predict the results of these experiments and spend much less resources on that. The problem is that in this approach, we lack data. Despite the fact that this cycle was executed several times, many data are still not of the quality that we need for training the AI. The classical modeling is a different story. There is an atomic structure of the material that's in the input, then the modeling is done, the simulation, so to speak, and the results of this simulation, that's the outcome. If we want high accuracy, we use the models that are being maintained by supercomputers. That's quite expensive, but it is becoming cheaper by the day, as I have told you already. And if we think about using AI, this is the molecular dynamics. The atom is falling here, and at some point it stops, and this modeling resulted in the prediction of some attributes that we're interested in. If we want to use AI for that, our first thought is the following. We have the outcomes of the experiments. We train ML model based on that, and we try to make direct predictions. The problem is that we still lack data to train ML models. I would wrap up here if I had no more ideas. But the more promising idea is the following. Let's use the ML training methods. Let's learn the physics. Let's machine learn the physics. This is how we're going to replace these computers, the supercomputers, with the models of AI. Now, what is happening on the physical level? On the supercomputers, we model with the quantum mechanics models. We have the cores of the atoms in a material that are described by the classical Newton mechanics, and we have light electrons that work in accordance with quantum mechanic laws. And the quantum mechanic laws cannot really be calculated with on a normal computer, so that's why we need supercomputers. As for the ML, the model is simpler. We do not need electrons to predict how the material will react to a pressure, to some pressure, some load. We need the position of the atoms, and this is a simpler model. And this is why the simple ML models are quite successful here and efficient here. Now, what have we achieved? We have our modeling diagram. The modeling is done based on the laws that the NN learned, and NN was trained based on the some 1,000 instances of data. That's not a lot. And as for the full-fledged modeling, we would need hundreds of thousands. So it works pretty well. These are the examples of our work, the outcomes. We have worked with MISIS, and they made a calculation of the mechanical attributes of the titan and nitrogen surfaces, the coatings, and they spent $40,000 and received the accuracy of 5%. And then we, using the ML, had the accuracy of 6%, and it was only $80, thousands of times cheaper. So that does not only mean that it is much cheaper, it gives you a fast feedback. Having very cheap calculations and computations help us to use higher level models. You don't need $40 million to get 1,000 instances of data to train a simple neural network. And depending on the task, it can cost around 80,000 to use the NN. Now, a small closed competition that was organized in San Diego, California. There were 4 groups from Cambridge, Skoltech, Bochum, and Germany, and Sandia, a national lab of the US. In 2 parameters, we were talking about the test error against the computational cost. And based on the polynomial power, the hidden layers were better than the neural networks, and NNs cannot achieve this level of accuracy because they need around 10 times more data than our models. It works absolutely fantastic to write papers and talk and sell your products to investors, but you can do even better. And the bottleneck here is the following one, is that we need to manually train the models that predict the physics. And the problem here is that is here on the slide, on this diagram. If we play a game, like we need to predict the energy of the interaction between the atoms, And for example, this is a simple one-way function, singular function. We interpolate that, and that describes the parameters much better on our interval. But if we did not guess with the intervals and we have to go beyond the interval, our model predicts something that can fully destroy the molecular dynamic principles. And if we worked in one dimension, everything would be great, but if we talk about 30 or 50 dimensions, something that is usually done, it does not work. So you need to train it manually many times, but instead of that, to automate the process, the entire process, you can use the active learning algorithms. And if we had a model that would predict what points were added in the process of the molecular dynamics, and that should be used to train, then the problem would have been resolved. It would be resolved. I add points. The model is trained based on that, and when the points are properly distributed, the next point will be here, will be added here, and then the model thinks that it should not be trained. The next dot is added here, and it happens up until the moment when we go beyond our area. What can happen? What effect will it have on our calculations, on our computations? So the algorithm will think that you should add dots here until everything is covered with dots. On the diagram, that means that we replaced the manual computation with some algorithm that is resolving it like that, and this is how the method looks like. This algorithm cannot decide what configuration to use for the training, the configurations of the atoms, but it receives the configuration from our molecular dynamics. It decides whether it needs to be described with quantum mechanics, and if needed, it trains the NN. If not, it makes the predictions. And this is how we get the properties. In practice, it works like that. We have some extrapolation threshold. There is a magical number from 1 till 10. You can select when this extrapolation error will be much more than the cost error, and we can continue that infinitely. And if we were doing the direct modeling, our costs will be growing on a linear basis, and we would not be able to use big data with the molecular dynamics. Now, how it works on real case examples, we used it in many projects. I'm showing you the lithium phase diagram. It is used by those who develop materials to determine for which conditions, and I'm talking about the pressure and the temperature here, we have the sustainable phases. We have 2 crystallic lithium phases and 1 liquid lithium phase.
This is all done by an AI-based system. Each point is long molecular dynamics, roughly 1,000 steps. We retrieve data from molecular dynamics, and we build the areas where different phases can be sustainable. The AI system does not only that, it also identifies flaws on the borders between the areas of sustainability, and it also helps us decide at which point we need to run molecular dynamics in order to be the most effective at reducing the error. This would give us the lowest number of calculations to end up with the dynamics. So in other words, it decides where you run your numerical experiment. This is the scheme of molecular dynamics that I described in the first part of my presentation. On top of that, we built this new algorithm. The input is the material. The algorithm then runs the molecular dynamics. It decides where it is. in which areas, and then there is another AI system which trains itself and is then computed in supercomputers. On the slide, you can say there is, in my opinion, a blueprint for the future where this industry is going, with different models, different methods of AI operating in different scales for our tasks and practical purposes, technically significant practical purposes. I would like to end my presentation here on this spectacular slide. Thank you, Alexander. We will continue with another difficult topic: computing singular values, impacting different properties of neural networks. Control over them can reduce unnecessary, undesired effects in training. I hope you will learn something useful for yourselves from our next speaker, Maxim Rakhuba, fellow professor at Higher School of Economics University. Maxim, over to you.
Всем добрый день. Меня зовут Максим Рахуба. Я являюсь...
Hello everyone, my name is Maxim Rakhuba. I'm associate professor at HSE University, and today I would like to describe the project we had with NUX in 2022, where we are developing a new framework for effective control over singular values in computational, in concurrent layers, convolutional layers. So the first area where this could be useful, the control over Lipschitz constant. We have a neural network. The input is an image, and then it runs a classification of it. The LNN in the top formula stands for the Lipschitz constant. If we are limiting the Lipschitz constant during training, say, the resulting neural network can have a better generalization capacity. It could be worse, though, if the Lipschitz constant is too limited, but it can also have a positive impact on the robustness against adversarial attacks. For example, if we add perturbance to the image, in theory, the neural network will be able to process it as something completely different, even though visually we understand that this is the same image. If the Lipschitz constant is not too big, with small perturbance at the input, the output should not have a lot of perturbance either. Now let's have a look at the connection between singular values and Lipschitz constant. Let's assume in the neural network there is this composition of simple functions, affine transformations, and small nonlinearities like ReLU. We can now use the known property for the Lipschitz constant of a neural network. The Lipschitz constant of a function composition is upper bound by the product of Lipschitz constants. As a result, thanks to the composition of small functions in the neural network, the resulting Lipschitz constant is limited by the product of the Lipschitz constant of nonlinearities and then the Lipschitz constant of affine transformations. And now let's look at the Lipschitz constant of nonlinearities. If we are using this widely used ReLU nonlinearity of an NN, the Lipschitz constant is limited by 1. Now let's move on to the transformation of omega x plus b. That's how you write fully connected neural network layers. If W has additional structure, the convolutional layers can also be represented like this. We see that the norm of Wx plus b minus Wx minus b is simple. The bias vector is reducing. And so this expression is equal to W by the difference between W and B. And that is the dominant singular value. That is the connection between the Lipschitz constant and the singular values of layers. Now let's look at the matrix of W in the case of convolutional networks. We have a convolution operation. We have an image in blue and a filter 3 by 3. We also have zero padding around the image with blank squares. So we take this filter, 3 by 3 filter, and we move it along the image. We compute element by element the product of the image and the blank squares, and we have the result. Same goes for periodic convolutions. In this case, we don't have this padding with zero blanks. So this is the convolution operation. In neural networks, we also have multi-channel convolutions, where the input depends on a number of channels. For example, as the input of our neural network, we have 3 channels. Cin is the number of input channels, and they are then represented as a certain number of images with a certain number of output channels, Cout. K is the filter size. So as a result, what we get is the transformation of the convolution is set by a tensor, the 4-dimensional array, K by Cin by Cout. That is the size. Now let's go back from the convolution transformation to the structure of the matrix. The convolution is a linear transform. Any linear transform can be written as multiplication by a matrix. If we take X as a long vector and do the same with Y, we will have a matrix multiplication represented as TC. TC is the convolution tensor. That matrix will have the size of output to input, so Cout n square by Cin n square, and it will have some additional structure. But if we do not factor in the structure, we will see very soon that this matrix is way too big, and it's simply impossible to apply a singular value decomposition. If we look at PGG 19, for example, and specifically one of its first layers, and if we use as the dataset ImageNet with images the size of 224, the size of the matrix will be 3 million by 3 million, and we will not be able to calculate the singular values. So we need to additionally factor in the structure of the matrix. The structure of the matrix was precisely what we included in our work, in our research in 2019. So what is this matrix built of? It consists of blocks with block circlets and circlet blocks. If you know what circlets are, good. If you don't know, no problem. I'm going to show you the algorithm now. We have the convolution kernel, C. The size is K by C by C. So Cin equals Cout, that's the assumption. What we do, first we increase the size of the kernel. We pad it with zeros so that the kernel could be the size of n by C by C. Next, we take the increased kernel. We apply discrete Fourier transform in the first 2 modes. It's simply done with the FFT function, fast Fourier transform. And then with the remaining 2 modes, we calculate the singular value decomposition. We conclude that the singular values in our matrix will coincide with the combination of singular values in the matrix that are in the last 2 modes in the kernel, where we did the Fourier transform. It looks pretty sophisticated, but the code looks very simple. NP FFT FFT2, the code of the kernel in the first two modes, and then NP linalg SVD with the remaining two modes. This algorithm has a clear and obvious problem when we are expanding the kernel, when we are padding it with zeros, and when we start applying Fourier transform, we are facing the challenge of memory. Big kernel, and also if we are processing big images or if we are working with three-dimensional convolutions, which is even worse, we have this problem with memory, and another problem with computing complexity, because it quadratically depends on the number of channels and the size of the image. What is our suggestion? We suggest decomposing the kernel using tensor decomposition. In the right top corner, we have the initial convolution kernel. It boils down to a four-dimensional array, but we have fewer channels, and we add two more matrices, U1 and U2. If you know how you mark tensor diagrams, this is what you see on the left. The four-dimensional array, the G kernel on the top with two straight lines coming out of it, and two matrices with two lines coming from them, and the connecting edge. If we use this decomposition of the convolution kernel, and if we additionally require orthogonality of the matrix U1 and U2, as you see in the theorem, we will be able to show that non-zero singular values of the TC matrix will coincide with the non-zero singular values of the matrix built on the smaller sized G kernel. So we are decreasing the complexity of the convolution kernel. And then you can use any algorithm to control singular values as long as you can maintain the orthogonality. In our work, we do it in several ways. We calculate the QR decomposition of the matrix, U1 and U2, and you can add supplementary regularization to maintain the orthogonality. Then you can metrize the singular values of the kernel using an algorithm of your choosing, or you can compute singular values and then you could clip them to 1. So this would be a step to singular values with desired properties. Let's look at how our algorithm behaves in practice. Here on the horizontal axis, what is plotted is the number of channels, and the speed up score belongs on the vertical value, on the vertical axis. We use the fast Fourier transform, and we represent different ranks in practice. What our experience showed is that it's best to divide the ranks by 2, 3, or 4. What we used in our experiments, if you look at the line that represents division by 3, the speed up of singular values is between 7 to 15 times the speed up. So this is the speed up of just one layer. Across the neural network, the effect can be unpredictable, or I will show you what it could look like. But first, let's look at more interesting experiments. These are the results of calculations when we trained the wide-res-net 1610 network. Baseline stands for cases where there is no control over singular values. If the rank is blank, it means that we're not using any additional compression thanks to tensor decomposition. And we see that in the case of the baseline, the accuracy is 95.52. But if we add tensor decomposition with the 256 rank, the compression will be higher, but the accuracy will go down. Now let's try to control singular values. If we clip them to 2, what we get is the accuracy goes up. Other metrics related to reliability and robustness, AAC, auto attack and CFARC also went up. And if the rank is 256, the accuracy is lower, but still it's higher compared to the baseline and way higher than the simply comprised network. As for the robustness metrics, it is even better than networks that control singular values but without compression. So this is the so we looked at the effect for a single layer and the network. Next was the experiment on VGG19. We also evaluated auto attacks, CFARC accuracy, and expected calibration error. The blue lines are where we're not using any additional control over singular values, and the orange lines is what we get thanks to accurate control over singular values and their clipping, as on the previous slide. The green one is when we also add decomposition. So the accuracy is higher than when we take the baseline or simple compression. To sum up, what we're offering is a framework based on tensor decomposition, a framework that takes advantage of the fact that neural networks contain an excessive amount of parameters. They are over-parameterized. Tensor decomposition helps us reduce the number of parameters on one hand, but on the other hand, you can also benefit from it to increase the efficiency and reduce the consumed memory when controlling singular values. And on top of that, you can use different methods. Just don't apply them to the initial convolution kernel, but rather the four-dimensional array. That's it for me. Thank you for your attention. Thank you, Maxim. I am sure your developments, your progressive experiments will be very useful for applied purposes. But without further ado, our next presenter, neural networks are actively used to tackle tasks related to structured data and image processing. We can get higher accuracy if we apply specific models of machine learning. This is precisely the topic of our next presenter, Dmitry Devyatkin, Associate Fellow Professor at Ivannikov Institute for System Programming of the Russian Academy of Sciences.
Hi everyone, my name is Dmitry Devyatkin. I am representing the Ivannikov Institute for System Programming of the Russian Academy of Science. I'm going to talk about the ensembles of nonlinear multivariate decision trees. Currently, the methods of training of NNs for the task of analysis of data and recognition of the images are used quite actively. However, there is a limited scope in terms of using that. The examples of these tasks are the tasks for the restoration of the images of MRI scans, the tasks of determining the 3D structure based on 2D images, the analysis of the tonality and sentiment of the text, when the small change of the text, the small change in with one comma in the sentence changes the tonality of the text completely. Therefore, the development of the discrete methods is very relevant, and these methods include the decision trees and their ensembles. However, currently they have some limitations. The limitation is related to the limited discriminative power, related to the peculiarities of built-in decision trees, and to complicated structure of the decision trees when you analyze the data with the large feature sets. The decision trees have to be optimized so that in the nodes there are splitters multidimensional splitters with several attributes, not only one attribute. These decision trees have to be put in the random ensembles, random forests, because these ensembles, they do not have limitations in terms of the complexity of the basic algorithms for analysis of the data that are included in the composition of the ensemble, and it can be trained on distributed computational networks, which is very important thanks to the development of the distributed computations. We started working on that more than 30 years ago. The first algorithms were randomized algorithms with low computational efficiency. On every step, only the parameters that could improve some of the criteria for the homogeneity of the data across the trees were maintained. However, the results of this research for such algorithms showed that these trees have a very low computational efficiency, and they cannot have low generalization capacity, and they cannot be trained with large arrays of data. Building random forests helped to drive up the interest towards this area, because the theory that underpins this method shows that the complexity of the basic algorithms does not influence the error of the entire ensemble, but the correlation of the margins of separate trees influence that. And based on these two areas of research, we can make the conclusion that the promising algorithm for building of the trees with linear and non-linear splitters can be used. And we should maximize the ensemble margin and minimize the margin correlation. And at the same time, we should use the greedy training algorithms to promote the decorrelation of the margins as part of the ensemble, for the trees as part of the ensemble. Moreover, the criteria on the heterogeneity of data were looked at. We looked at the generalization capacity of the trees, and it was determined that the margin affect the accuracy generalization, and the users of the algorithms should create these criteria themselves. An important factor that improves the generalization for the trees is the margin between the data in the upper parts of the decision trees. As part of the scientific effort to build the trees with linear and non-linear splitters, in the last several years, a couple of dozens of papers were published. However, they did not meet the criteria that I talked about on last slide. So either the margin is not optimized, or you cannot set a criteria about the homogeneity of data. Moreover, in many algorithms, the loss functions are quite difficult to be optimized. They cannot be used to train large volumes of data, with large volumes of data. Many of the algorithms are not greedy as well, which is not great to use that in the random forests. Therefore, this is still relevant. The goal of this paper is to develop the method of training forests with oblique and kernel splitters based on all of the criteria I have mentioned before. The suggested algorithm on the higher level replicates the CART algorithm on the high level. If data includes only one cluster, the algorithm completes its work, it ends. If no, then some distribution of classes is generated among the subtrees. It is generated by the minimization of the criteria of the heterogeneity of the data that is set by the user. If we don't have a lot of classes, then the specific solution is found. If not, the greedy algorithm is used, and then the distribution, the set distribution, defined distribution, is used for the classifier that distributes all the objects of the analyzed data across the subtrees. The support vector method is used there. And we look at the classification method, and with it we decompose the set, and the entire algorithm is being repeated. On the right-hand side, you see an image, the one to the right. This is where we use the support vectors method with the slack variable. And on the left-hand side, without the slack variable, we use the Genie to support that, and we can see that if we use slack variable, there is a heterogeneity of the data in the blue area. How do you build a binary classifier? We use the support vectors method with the scale of the slack variables. They're being scaled up until the point when it leads to the heterogeneity of the data. In our algorithm, we have set the distribution of the classes according to the subtrees. It is not possible to find the global optimum for the criterion of the heterogeneity of the data, and there is a descent of the graph of the criteria of heterogeneity of the data towards one of the local optimums. On practice, since it's a greedy algorithm and the trees are used in random ensemble, the ensemble of the forests of the decision trees, that means that achieving the minimum, only the optimum minimum, does not decrease the quality of the results. At the same time, the speed of the training increases dramatically. Then the experiments showed that the decision trees that we receive can be retrained vigorously, and this is why we decided to use the procedure of decreasing the complexity of the decision trees. The forests of the classes that were formed in the leaves of the decision trees that were used by the original algorithms were removed, and we used SVM task to optimize the weights. And then the empirical risk for the entire ensemble was minimized, and moreover, we minimized and regulated the newly generated weights. The regularization parameters helped to set up the generalization capacity of this amplification. And the second step of this process, we removed the vectors of the generated classes for the leaves for which these vectors were quite similar, quite nearby. Talking about the Euclidean metrics. The number of leaves in the trees decreased and their height decreased, and therefore the decision power of the trees of the ensembles and forests improved. Deep forest is a cascade of forests. Have several layers, a sliding window to generate features, and it has the vector of the weights that coordinates with the vector of the source attributes, and it moves to the next model, to the next random forest that has a larger set of attributes. Using this approach to help to increase the accuracy of classification up to some point. However, this method has some drawbacks. The instability of the results, first of all, because it's related to the fact that apart from the random forests, there were extreme forests that were used to improve the decision-making capacity. And the card trees meant low efficiency in terms of the big data analysis with the size of attribute space. As a solution, we decided to use the algorithm with the for the forests of trees with linear and non-linear splitters, oblique kernel splitters. It helped to increase the accuracy of the forest method, and it helped to decrease the instability, because this is how we were able to improve the results. Now, the results of the experiments, we used two sets of groups of data, the UCI data set. These are quite large data sets that are working for the image recognition. These data sets have quite a low, have a very high MNIST, 784 features. CIFAR-10 is a big data set, and these data have a big size, more than 3,000 features. That makes the use of the forest-based method quite difficult, because there's a lot of data. So we were able to show that the kernel forest maximizes the accuracy and classification of the random forest, and the decrease of the complexity of the forests, of the trees, helped to increase the accuracy of the classification by more than 1%. There was also an assessment that was done in terms of the time for the training. There was an analysis made, and for the oblique splitters, the algorithm for building the forests is the same as with the forest with splitters, and we also got some practical results using the data with the size of attribute space. We used the suggested method and the classical decision forest method. We showed that there was a theoretical linear assessment and estimation. I mean, that resulted from that. And apart from the methods of building the decision trees that we were comparing with, they have a asymptotic complexity that you can see on the diagram. That means that the algorithm that we suggested for building the univariate trees is good for big data. On the second stage of our experiment, we looked how using deep forest can improve the quality of the classification with the same data set. It was shown that on all data sets there was a great improvement in terms of the accuracy of classification. It was also compared with the actively applied architectures like AlexNet and another one, and ResNet. We showed that the observed data can be compared with the results of ResNet. With CIFAR dataset, with the big size of the attribute space, there were no results still. So it's still relevant to improve this method to increase its accuracy. To wrap up, I would like to say that the proposed algorithm is in line with all of the criteria used to build the decision trees with oblique and kernel splitters. The experiments showed that the use of nonlinear kernels improves the accuracy of classification on many data sets. Moreover, the used method of strengthening and decreasing the complexity of the ensembles of the trees showed its applicability for the optimization and improvement of the trees with oblique or kernel splitters. At the same time, we showed that using the kernel splitters with big data, the speed is not good, is not enough. So it's still relevant to develop the computational efficient methods of the double optimization of dual solvers for problems with slack scaling is still required, is still relevant. And that's it for me. Thank you for your attention. Dmitry, thank you very much. I think that we should go with the same tempo, and we're going to our next speaker, who is going to present DeepPavlov dream. Quite romantic. Does that mean that the dream of many researchers came true? Well, we are going to know that. The deputy head of the lab for neural systems and deep learning of MIPT, Dmitry Kornaev, is going to present the DeepPavlov dream. Ladies and gentlemen, it is a great honor for me to present this material on AI Journey 2022. Last year, in AI Journey 2021, I talked about the DeepPavlov dream journey, going from NLP models to the development methods used for AI that can talk. And today I'm going to talk about our next big step in robotics. In our that we developed in our lab under MIPT. Now, why do we need AI assistants? Many can think that assistants started from Siri on iPhone. The idea is that the computer can augment the capabilities of human brain were first voiced in 19th century. Then Senvarro and Bush published an article in USA Scientific of 1945 that supported this idea. Then the agency of the prospective development under the Defense Department of Defense of the US were publishing the papers on that in 50s and 60s. But then Xerox PARC was created in Palo Alto in the 70s, and this idea started to be actively developed. The personal computer called Alto was developed, and the visual interface was developed for it. What you see is what you get, type of interface. What you type is how it is going to look like. The icons and the desktop and the windows were created there, and this was the moment where the open user interface was created. In 1981, IBM delivered IBM PC, and then there were some clones of IBM PC-like computers. Although Xerox were not able to develop this with Alto, it produced the Xerox Star computer in 1981. The commercial success was enjoyed by Apple, and then those who developed PCs based on Windows 95. And it is the appearance of the open architecture of the hardware and of the software led to the great leap forward of our entire industry up until today.
But Xerox didn't stop there with PARC. In 1991, their leading scientist, Mark Weiser, published another article in Scientific American about ubiquitous computing. His idea was to have computing devices be ubiquitous everywhere, so we could seamlessly transition from one device to another. His idea was that all computers would be connected in a single network, and each system controlled by user computers would adapt to changes and would help users perform any tasks at any computer, at any device. He thought that there would be a new type of devices, devices that we now call smartphones, tablets, smart displays. Anyway, there is a huge range of all kinds of devices, and this simplified switching from one device to another, and this means we have new problems that we need to tackle. DARPA supported this idea back then in the 90s, but in the noughties, this idea of ubiquity started appearing everywhere, developed everywhere, in Dartmouth and elsewhere. DARPA Kalo project for a cognitive trainable assistant that spans across all devices of a user. From that, we transitioned to the concept of smart assistants for users, Siri, Alexa. From that, we transitioned to the concept of surfaces, smart watches, glasses, what have you. Then we focused on assistants, mainly controlled by voice, but voice assistants are limited, way too limited. They don't know when we are addressing them, other than the cases where we directly call them by name. They don't understand when we are silent, when we are taking a break. Are we going to resume talking? Are we smiling? Are we laughing? Are we crying? Are we talking to them or to other people? The dream of creating a perfect virtual assistant is associated with another project, this assistant for the kitchen. But zeros and ones are simply not enough at the moment. We need more complex interfaces. 99.9% of AI assistants problematic has not been solved. At DeepPavlov, between 2017 and 2021, we've been working on personal assistants that can talk, that can be controlled by voice. We learned through the Alexa Prize Challenge how to perfect our algorithms. The challenge is for the best of the best among all universities and research teams. The goal is for the robot, for the assistant, to maintain a conversation for at least 20 minutes and get an average rating of at least 4 out of 5. This is very ambitious, very difficult. When we participated, the winning team got the result of 3.8 out of 5. But the length of the conversation was only 7 minutes. In 2021, last year, when we once again participated in the competition and we were once again in the semifinals, the winning team from Czech got the score of 3.28, but the length of the conversation was bigger. We participated in other conferences, AI conferences, and presented DeepPavlov in 2020. After participating in Alexa Prize, we realized how big the problem is faced by those who would like to create an AI assistant. And we developed this vision of how to build the stack of all the necessary technology. In the summer of 2020, we started our work, and at the end of 2021, we launched the first version of our open platform, DeepPavlov Dream, the system that allows any company in the world to build their own assistant on a par with Amazon or Google assistants. DeepPavlov Dream incorporates our DeepPavlov library and allows creating assistants of Alexa or Elisa grade assistants. For that, we created our own engine, and by now we have had almost 500,000 downloads of that version. We have almost 6,000 stars on GitHub. The core of our platform, DeepPavlov Dream, manages more than 60 servers, and according to our estimates, we could grow to 100,000 requests per second. Our NLP models are used in the US, mainly in production, in the cloud by Amazon and Google, and in Russia, the most demand is among educational institutions and in Yandex Cloud. we're happy to say that we have built a system that helps create abstraction on top of various solutions and that helps users perform their tasks thanks to talking AI. One of the biggest innovations we created is a DeepPavlov Dream Builder, where you can build, similar to Lego builders, your own assistant. In addition to voice-to-text assistants, we did something else in the summer of last year. Together with MIPT and Spur Devices, we suggested the next step to go beyond text and voice. The step towards assistants that can see, hear, and perform in accordance with our requests. Assistants that could live in virtual and physical environments, assistants that can help us anywhere. This is how we devised this vision of our AI center. And this is where we expanded our vision of assistants. Adding the robot scheme on top of it could look like just a small square, but it's much more than that. We focused on new applied research and we incorporated the work of other labs on the platform of MIPT in our work. Among those developments are emotional artificial intelligence, because the robot needs to be able to recognize human emotions and be emotional itself. The personalization, the robot should identify the user. Strategic identification of user goals. Robot should also have its own goals. Control over your robot should not be a black box, and multimodality. This is where the assistant has the body of a robot, can recognize the environment, human emotions, manipulate objects in the physical world, etc. A couple of examples, what we did over the past year. First is the integration of our Dream Assistant with the STRL Robotics of the Center of Cognitive Modeling that is working on the platform of MIPT. This can perform various commands. It can open doors, rotate counterclockwise 60 degrees. Rotate to the right 40 degrees. Move forward 1 meter forward. Move 2 meters back.
Повернись против часовой.
Rotate 200 degrees counterclockwise. This is an integration of DeepPavlov Dream and STRL Robotics of the Cognitive Modeling Center. These are our first steps towards integration with other labs in our center that develop human-like robots and driverless cars. In this video, we are showing our assistant within Minecraft. Minecraft is a virtual environment where the robot cannot harm humans in any way, in any situation. So we can safely simulate a robot interaction with humans. This is where the human is training the robot how to build a Stonehenge, and then we tell the robot to build a Stonehenge in an empty field. If we scale it up to more complex virtual environments, this is basically the approach of digital twins. In conclusion, I'd like to say that in the market of talking AI, there are a lot of solutions by startups and big corporations, but we were the first ones to bet on multimodality and robotics. Thank you very much for inviting me to AI Journey 2022. I encourage you to create your own AI assistants for your robots using DeepPavlov Dream. with STL Robotics and the Center of Cognitive Modeling and other AI labs and centers in MIPT. Thank you. Thank you, Danila. I'm so happy to see that all the speakers, same as celebrities of intellectual Hollywood, are so enthusiastic and would love to talk about their research for hours. Once again, we saw that artificial intelligence is rife with opportunities for change. We continue. The next speaker knows all of this firsthand, the researcher of AI lab in healthcare, Alexey Kornaev. He's representing the Innopolis University, which is leading and takes an anchor place in HR resources for digital economy within the national program Digital Economics. Alexey suggests using neural networks for modeling hydrodynamic processes. Alexey, the floor is yours. Hello, colleagues. My name is Alexey Kornaev. My presentation will be about theory-based machine learning and its use in hydrodynamics. 5 parts of my presentation, including mathematical modeling, simulation modeling, and so forth. It's been long observed that out of all the possible areas of process vector, there is this minimal value, the principle of least action, for example, according to which out of all possible options of movement, the natural one is the one that corresponds to the least action. The basis for such approaches, such laws of retention, are the calculus of variations. The essence is as follows. In the process of solving a problem, you need to identify the values of unknown functions that ensure minimal functionality. And also, if the manifold of functions can be represented as the manifold of values, so then we are talking about a set functionality. These are examples of known problems, such as the brachistochrone task. Among the many functions of a body, we need to set the trajectory that corresponds to the descent minimum. So we know the solution to that problem. Or another well-known historical problem, out of all the possible functions limiting an area, we need to find the function that ensures the maximum area, but with a limitation in terms of the length of the perimeter. The line is closed. The solution to that problem is a circle. If we segue from the physics, hydrodynamics, to hydrodynamics, without delving into the functionality and its relation to power, we can arrive at an idea of how the solution is found out of the possible options of the speed function, represented in the left-hand part of the slide. We can select power series, different dominant powers, different parameters between 1 to 0. We go through all these options of velocity and we identify the one that ensures the minimal functionality. We are not yet saying which functionality. And then in this case, if the function is represented as a series, it is no longer functionality, but the functionality of energy, but rather the functionality of the many parameters, the theta parameters. Selecting parameters is a standard task for machine learning. In mechanics, in hydrodynamics in particular, there are other known, more traditional approaches where the solution of a problem is produced through a lot of differential equations, including derived equations, up to 20 equations with 20 variables. Applying modern finite element systems such as ANSYS, we could solve problems as such. We could divide the flow range to finite elements or control volumes or sample volumes and identify end functions. This is very complex and very expensive. It turns out that machine learning can also be a solver of such problems in physics with different degrees of implementation of ML. The first option, the most straightforward one, is when in machine learning we do not fix any natural basis. For example, we have this solid environment, air around the wing, there is this wing formula, and within the area there is the wing. We need to identify different areas of physical metrics, the velocity, pressure, other metrics. This is obviously a complex task. The first option for solving it is using supervised training. We know the input, the images of the wings, and we need to minimize the error. The typical approach is to simply minimize the error, no physics. Another option, more complex, higher level solution in terms of physics. The functionality of the error, to that we add a summand that has a physical meaning. In this case, it could be the difference between the left and the right parts of the differential equation. And if we know that the solution is correct, the left and the right parts are the same, so this addition should equal 0. This is an example of conditional optimization with the 0 added summand. So in this case, machine learning occurs in a more physical sense. And third option is the option that we explore in our work, is using as the minimized function a physical expression. As I said in the beginning, it could be an expression for, say, velocity. These are the results of other researchers who also try to solve the problem of elastic deformation. In the process of solving it, you need to identify displacement fields, strain, etc. So the idea is that as loss in machine learning, what we have is the functionality of energy. For that functionality, we set a multi-order functions, which you see on the right.
And they're on the edges, so they are variable. They variated with the neural networks within. And on the edge, they are reset. And with the neural network, we select the parameter, provides a solution. For the hydrodynamics, this approach with the reset on the boundaries, on the edges, is not working because the functions of this type cannot describe complex boundaries of liquid moving related to vortexes that happen sometime. However, the idea is the correct one. In this research, we were focusing on trying to find the physics-based loss and the functionality, the minimization of which will be in line of the resolution of the problem of the application of non-Newtonian and real magnetic fluids flow modeling. So this was the goal. And the problem was that to think about that loss, we need to make sure that it is in line with some physics, law of physics. So finding the this loss should be reasoned. There should be a reasoning for finding this loss. Now, two options again. Either you can resolve the differential equations. These are the examples of the differential equations. These are for stationary states with the and the number of equations can be decreased from 13 to 4. This function of the velocity with 4 components, and the problem is that if we think that there is a Newton liquid the viscosity of the liquid is the capability of the liquid to resist the deformation. If the deformation of the liquid is done slower, when you put a liquid from one vessel to another, if the deformation is slow, the liquid starts to resist, and the viscosity and the resistance can increase quite rapidly. And there is a nonlinear relation with the speed and the deformation and the viscosity, and this effect had to be taken into account because Newton liquid is something that we were looking at, and Newton liquids were particular cases. Now you can develop a functionality, the minimization of which can be the resolution. Now there is an approach in mathematics that can help us to check the functionality. So you can write down the functionality as an integral, and for the integrated part, you can use the Euler's equation. If the Euler's equation meet the classical problem, then the functionality is the correct one. This is a heuristic approach of selecting the functionality when every choice can be checked. As this task was resolved, as we were resolving this task, this problem, we had to generalize the Euler's equation. That's what we did, basically. There are limitations in Euler's equation. You know, the variable function should be fixed on the borders. On the right-hand side of the slide, you can see that. This can be generalized as well, this limitation, and you can make it less stringent. Then we took the functionality that we know, the Lagrange functionality, and that has this limitation. It's on the slide here. That means that non-Newtonian fluids cannot be taken into account. So in our suggested functionality, that's the current, the rotor function, that is the main unknown. It is the vector of speed, of velocity. That functionality is in line with the source physics equation, the transfer of the vorticity transfer equation. Now the realization of this approach was as follows. There were several options for the realization on how to minimize this functionality, and the first thing that you need to think about is to make a multi-layer perceptron net and put the point locations and the environment area on it, and this coordinates with linear and non-linear transformation that happen in the net will be transformed in the value of this unknown function of the current in this node points. Knowing the function, the value of the function of the current, you can determine the velocities function, that's the rotor of this function, and then you can calculate the values of the functionality that should be minimized. And then there is a very standardized gradient calculation, standardized for ML. The unknown parameter values are being determined, and this is repeated up until the minimum of the functionality is found. And the minimum of this functionality, based on the hypothesis, the minimum will be the functions that are real or close to the real ones. And the second approach, resolving the same task, is lower requirements, because in the previous case we had to divide the space and to build the grid, the net for this space. And the second option is simpler. What will happen if you if you transform the source image and transform it in the same image, but not with on a random field of function, but the one that corresponds to the minimum of the functionality. Now, UNet works great here. The algorithm is more or less the same, but the differentiation is done according to the image. The speeds are selected like that. The integrals are calculated like that, and this is how this method is sensitive to the equation, and but otherwise it works in the same manner. Now we looked at the movement between two parallel plates, and we looked at the liquid subject to magnetic forces, and this liquid must be geomagnetic. We made some computational experiments, and we understood that the observational error is 7%, and the resolutions and the solutions are the same. There are options to decrease the observational error. Then we looked at the other case, where we looked at the liquid that was moving through the narrower or wider spaces, and this approach worked. We used the images that was received thanks to capillaroscopy. These are the capillaries on the surface of a nail wall, and we took the image that was made during the experiment and received the full distribution of the velocity and of all the other mechanical characteristics of the movement of the blood in the capillaries, and that was very pragmatic, and we were able to check whether the method works. There are some requirements to the resolution of the image, but these requirements can be met. Now, these are the major pros and cons of the approach. The major pro is then that this is a universal approach. The code is very simple. Cannot be compared with the complexity of the ANSYS code. However, there are some limitations. This approach cannot look at the stationary tasks. So for the non-stationary flows cannot be processed by this solution. Now, as for the other pros and cons, you can see them on the slide. One of the promising areas for developing of this dynamics is working solution is working with MRIs, a movement that look at the movement of the blood in large vessels of the human body. Thank you very much for your attention. That is it for me. Thank you very much. Alexey Kornaev was with us, and I'm looking forward to invite Ivan Khodnenko, the research fellow of the lab called of the intellectual technologies of making decisions in ITMO University. Is going to present a cloud platform that is available to the larger public. You don't need to be able to code or to install any software to use it. I think many will not believe that it will be it is achievable in such an innovative area, that you can use it in such an innovative area, and it can be used for high-tech manufacturing. Thank you, Anastasia. Hi, everyone. My name is Ivan Khodnenko, and I'm going to talk about the visual coding. And we will start with the coding. What is traditional coding? You code in a traditional way, and then you use it. You use it for the software. You use it to build the software. You use the blocks, and you achieve the result. This was called low code. And no code is when you use a builder, and you can write some code there, and this is more for some specialized areas. Now, actually, quite a lot of stakeholders are involved in visual programming. There are many products in many areas, and this is 1996 stats. Starting from 1996, the no-code products is increasing rapidly, and we have a statistics for these products, and the leading positions, the leaders are, there are new leaders all the time, and the research confirms that people actually use these tools for research, and this, I mean, there were many reasons. I'm not going to talk about all of them. This is why we decided to develop our own product, and first of all, we wanted to focus on automation and improvement of the performance. Everything should be as intuitive as possible, and the platform should help you to select the actions and to augment some of the actions. Quality, development quality, the quality of the model being developed, and the quality of the process of the development of the model. That's very important as well. Now, there were some threshold limitation for the limitations, and we mostly work on the classical ML tasks like classification and regression, and these kind of things. We are not really in NNs. Now, as for the architecture, graph is the foundation. It is configured with a web browser that works with other services to handle the model, to create the model, to draw the graphs for these models, accounts for the users. It connects with the compute resources where the models are being computed and calculated, and it uses APIs. Now, the bipartile-oriented graph is the main component here. There are two nodes, the model node and the data mode. Data mode node is responsible for everything related to data. The model node, these are all models of the kernel, the pandas or other nodes that were uploaded to the model. And the graph, the computational graph is built and the computation is done. And I'm going to show you how the model works. And what can you see here? There are many projects here, and there are models for creation of models. There are templates for creation of the models. Now you can put any name. There are some prompts. You can you are not required to read them, and then you create a data set. After that, we can move to the editor. We create a couple of nodes. The data node is created by default, and now we can connect them. We can look at the attributes near the data. Everything is fine. There's no need to delete anything. The second node shows an error because there's no reason to connect two nodes. So we can select a model, and then we select a logistical regression, for example. We select the model, we push save, and then we hit compute. And we go to the calculation panel, and you can see the logs and the results. You can see the qualitative metrics table, and you can look at the diagrams as well. So these are the attributes of the model. Now moving next, for a more detailed demonstration, we're going to look at a specific example. For example, we can take give me some credit dataset, where you have to classify whether a loan should be given or not. Now, there's a lack of balance. That is, there are imbalance-related outliers and some spaces that. First of all, we create a table where you would put the name of the hypothesis, name of the experiment, some individual characteristics of the model, and the quality metrics, and then you would give the links for Google Colab or something else, or some other notebooks. It can be synchronized with GitHub, for example. And this is the development process that is, well, basically standardized. With Smile, your life becomes easier. And you should try that. First of all, you need to create a project. The project is the representation of the task. You set up the project, you can add the team members, then you create a model when needed. So a specific case, specific hypothesis, specific experiment. First of all, you need to create some baseline. It is done automatically. You can automatically build a baseline with minimal data processing, and then you will have some quality of the model, the minimum quality of the model. Then the AutoML recommendations will be introduced. You will receive some prompts if you are a rookie here, and then you can have some resulting table.
We add a window on a website where you can select the points that you need after the analysis of the current graph and current data. It adds parameters that it wants to add, or you can check the boxes for the parameters that you want or do not want. Then the computational graph is built, and after that you can start the cross-validation module and look at not just the modules but the confidence intervals for different metrics to make sure you get a quantitative estimate with a higher quality. Let's say it's late at night, you need to go back home from work, so you can start it and leave it running overnight. And in the morning you will have the result. This is the example with FDOT, with composite graphs, using the graph structure that we translate to our computational graph on. As the output, it has this optimal combination of graphs, lots of yellow rectangles. So as I said, you can leave it running overnight, and in the morning it will give you the result. It can be easily interpreted. You can see the nodes that it added and the parameters it added. That could be your starting point in developing your own solution if you see that the solution can be improved any further. There is a recommendation system, of course. That's what I said about the quality of development, especially pertinent for newbies, for people without much experience in this, so that they could have prompts or tips or a checklist to make sure that you're using not just a model for training, but that you're using cross-validation to assess quality, to make sure your model is not overfitted, there are no errors. The recommendation system will prompt you to check item by item whether you did everything correctly, and last but not least, you'll have the space of modules in front of you, and you'll also have the spreadsheet with the models that are best. And while the mean score is calculated, this functionality is still in development. We have something on the screen, and you can even see that some modules are null, but anyway, this is to make sure you have the confidence interval, and you're able to compare confidence intervals between different models and do your quality assessment correctly. As an example of what I was saying, this is this slide. The project is a bank scoring model. We have been versioning the solution, but anyhow, you can see that there is a version where there is just one model. There is the 7th version of the project with the most modules. You see everything that is possible here in this model. The module of machine learning, divided by train and test, cross-validation module with validation of single data, bootstrap. No differences between them, but the key idea was to combine all modules together. And as you can see, as you can verify, as I was saying, there are different tips for the developer, reflecting everything you might need in your work. Of course, you can add some other things to it, but still, this is a good start. No, check this tool online. It exists, but only virtually. A couple of examples. How have we been using it? We did not just develop the system for no reason. We had practical use cases in mind, and we've been customizing it. One of the tasks is related to urban development, the city of St. Petersburg, where we wanted to create a classification model to assess the quality of facades. This is not just cross-validation. There are a lot of modules in this model. They remove duplicates, they identify more correct class values, they do the filtering, they normalize data, they identify additional attributes. The result was a model for not the entire city, but a region of the city, but by quality it did satisfy the customer. Neural networks and primarily image processing. This is where not just models, but different modules of transformation and augmentation can be used. This shows what you can see in the process, the different interim stages. It doesn't mean that you can create your own neural network, but it means that you can take an encoder and additionally train it. This is now available in translearning, and we do not want to move away from it just yet. The idea for now is to validate a hypothesis very quickly using standard tools. And if you have a more complex model, it's best if you develop it yourselves. With this, you can tune epochs, you can play around with the different parameters, and get your scores, visual scores, and numerical scores. A few more examples of other platforms, 3 most accessible platforms, in our opinion: KNIME, SAS, and Orange. They have their pros and cons. KNIME and Orange are completely open source. SAS is subscription-based. We took them for a test drive, and Orange was our favorite. The most user-friendly interface, intuitive development. SAS offers you, we believe, too many of their own elements. It is excessive in that, and KNIME is excessive in terms of nodes. Orange, we think, is the best, a bit lacking in functionality, some flaws here and there. Well, nothing is without flaws. If you'd like, you can also check them out. Thank you for your attention. That's it for me. Once again, my name is Khodnenko. I encourage you to check out the platform and send us your feedback. Thank you. Thank you, Ivan. I myself tried to test drive the platform behind the scenes. So many distractions. Someone was filming me, I think, bloggers maybe, but no bloggers here, just researchers and scientists. The final block of the short session short talk session about video compression. Sergei Lavrushkin, the researcher at the Institute for Systemic Programming of the Russian Academy of Sciences. As far as I know, Sergei has extensive experience in studying various perturbations and biases and how they affect your comfort as a viewer, and using neural network algorithms for processing and compression of video to improve its quality. Thank you, Anastasia. I'm happy to welcome the participants of AI Journey 2022. In this presentation, I'm going to talk about the results of this endeavor to create a new benchmark for improving the quality of video processing. This is a joint project at our university, together with Lomonosov Moscow State University. So we are focusing on video compression, video processing. We have 15 years of experience under our belt in video compression. One of the most prominent projects of our lab is annual comparison of video codecs involving companies that develop these solutions. We also have a lot of experience in assessing the quality of video. In our group, we have the VQMT software tool, and we've also been working on various benchmarks and studying different ways to assess the quality of video. This year at the NIPS conference, we have submitted our paper about the new dataset and benchmarks for learning-based video quality metrics. Let's review the article and our research. At the moment, video content takes up the biggest internet traffic, and this share continues to grow. This trend is also prominent in mobile traffic. We see an related increase in network load, which means that developing new standards of compression are particularly pertinent. The new compression standards are serviceable, but when developing new standards of compression, we need to use metrics for assessing the quality of video, to assess the quality of the output, and to compare with other methods. New video quality assessment methods are becoming more and more numerous. New approaches based on machine learning and neural networks are emerging. Most new methods are trained with old data sets, with old compression standards, which means these methods are not applicable with new standards of compression that are using newer neural network approaches. I am showing the example which illustrates that older algorithms, older methods are worse than ML-based algorithms that can recover more detail. The goal of our research is to study the applicability of new methods in compression tasks using newest standards of compression. And to achieve that goal, we suggest a new set of data consisting of 2,486 compressed videos with subjective scores associated with each video. And based on that data set, we have conducted a large-scale study of objective quality assessment metrics with benchmarked and non-benchmarked methods. Let's review the data set. The data set included 36 high bitrate videos selected out of 18,000 videos extracted from Vimeo, EXIF, and YouTube UJC. We tried to cover all possible cases with spatio-temporal clustering. The average length of the video was 10 seconds. The final dataset resulted from compression of initial selected videos across 7 compression standards. We reviewed 3 preset parameters for compression and 3 target bit rates to cover all possible perturbances. The resulting dataset was divided into open and closed parts, 40 to 60% respectively. The closed part is used for testing methods with our benchmarks so that the tested methods could not be retrained for our dataset. The image shows the distribution of resulting bit rates in the 2 samplings according to this parameter. As you can see, the samplings have similar characteristics. We have also been collecting subjective assessments. Thanks to subjectify.us, we would show viewers pairs of videos generated from one initial video, original video, and the viewers were supposed to choose the video of the best quality or to say that the quality is the same. That way we collected more than 10 responses for the video pairs, all in all more than 766,000 valid answers. And then the answers were converted through the predatory model. If we compare the proposed dataset with the existing analogs, we will see that we are using a large number of codecs, and we are covering all kinds of compression deteriorations, while analogs mainly review H.264 standard. Also, in the resulting dataset, we have a lot of responses from a large number of people, which means the subjective assessments of the videos are pretty reliable. The open part of the data has been published. It is available for downloading using the link on the slide. And now the benchmark. Thanks to the datasets, we have reviewed 12 full reference and 15 no reference metrics. The results were provided for the entire dataset and also the subsets by different compression standards, different bitrate ranges, and video types. In order to identify the applicability area for different metrics, to range the quality metrics, we identified the correlation by Spearman and Kender as subjective assessments were resulting from pair review of two videos extracted from one original video. We see that the correlation coefficients were calculated independently for each video group, and then they were averaged and transformed into a single score through Fisher transform. Also, while we were comparing, we factored in the color metrics. To do that, we would take the results of the metrics together with the color components. Speaking of similar benchmarks, you will see that most of them were developed for publication, and after publication those benchmarks were no longer maintained or updated. Out of the updated benchmarks, we only found one UGC VQA, but with a benchmark we saw that a small number of perturbances in compression were reviewed, and the researchers only focused on non-benchmarked metrics, while our proposed benchmark reviews all possible perturbances, benchmarked and non-benchmarked metrics, and we also have a closed part of the dataset. The results of the research are available. The link is on the slide. And now the results of our research. This slide shows the outcome across the dataset. You can see that modern no reference, no benchmark methods are catching up with the traditional methods and are even ahead of them. The best method for assessing the quality of compression is still the Netflix metric VMAF, but the neural network non-reference, non-benchmark method MD-TVSFA is very close by correlation assessment quality. If we break this down by categories, the linearity metric is best for assessing the quality of compression using the VVC standard. It is ahead of the existing benchmarked methods for compression quality assessment. We can derive the conclusion that traditional methods are worse than the newer methods for assessing the quality of compression, such as VVC and AVMen. The benchmark also factored in the speed quality setup. To do that, we would measure the speed of method performance with each video. 3 measurements. The measurements were done on a computational cluster with the configurations shown on the slide. Let's review the results for the speed quality evaluation. Traditional metrics for assessing the quality of compression. VMAF, MS, SSIM, and PSNR are still optimal in terms of speed quality performance, and for a good reason, because these are the most popular methods, and the research in that area continues, in particular research as to how to accelerate their performance. But the non-reference non-benchmarked methods are catching up with the optimal benchmarked methods, so additional research and additional acceleration of these methods could make them too optimal for assessing the quality of compression. So in my presentation, I tried to describe our proposed benchmark for assessing the quality of video compression. This benchmark is based on a new dataset in which we tried to include all kinds of biases and perturbances in compression. We have already received 4 more requests for adding new metrics to our method. We have received largely positive feedback from large corporations, from researchers. We continue our research and we continue expanding the dataset and adding new methods in our comparison. Thank you for your attention. Thank you, Sergey, for that unique experience. Sergey Lavrushkin was online presenting. I would like to once again thank all the speakers that presented during the keynote part and the short session part. You have given us the energy and knowledge to carry on, but this is not the end. We will have a short break. Let's have a cup of tea, black or green, or maybe a cup of coffee, or just the most delicious cup of water. Short break and we will resume.